Hey, it's Mr. Lum again, and we're going to be doing the January 2003 provincial exam right here. And what we're going to be doing is we're going to break this provincial exam down into the various different units. So first, today, on this video, we're going to be doing Unit 1 questions only. So let's get started. Scroll down to our first question, and it says, given the reaction, we have calcium carbonate plus HCl, or hydrochloric acid, and it's making calcium chloride, H2O, and carbon dioxide with some energy, with some heat. And the question says, which of the following will cause the reaction rate to increase? Now, we're not dealing with an equilibrium reaction right here. We're dealing with something that is just going forward. So, increasing or decreasing pressure. Since our reactants are solids and aqueous, and we're not dealing with gases, this has no effect. Okay. Now, decreasing temperature never increases reaction rate. Okay, and that is for like the collision theory. If we increase temperature, what is going to happen is particles are going to be moving faster, they have more energy to collide, and therefore reaction rate is going to increase. So increasing temperature will increase reaction rate. So our answer is 1C. Number 2, which of the following consider the following reaction. What we have here is, it says if we have 0.5 moles of iron is produced in 10 seconds, what is the rate of consumption of Fe2O3 in moles per second? So what I'm going to do is I'm going to take iron, which is 0.50 moles, and I'm going to change this into moles of iron oxide, or iron 3 oxide. And how I'm going to do that is use my molar ratio. It's a 2-to-1 ratio. So I'm going to times this by 1 Fe2O3 over 2 Fe. Okay. Now what I have here is I have moles of iron 3 oxide. Okay. But my question is asking me rate of consumption of moles of iron 3 oxide per second. So what I need to do is, the reaction is happening over a 10-second period. So I'm going to divide this by 10.0 seconds. Okay. If I do this calculation, right here is going to equal, this top part is going to equal 0.25. And then if I divide by 10, my answer is going to be 0.025, or in other words, 2.5 times 10 to the minus 2. And that is my rate of consumption of iron oxide. Number 3. Which of the following would result in a successful collision between reactant particles? So, if we have particles have sufficient kinetic energy, that is very, very important. Okay, but a more important, like a thing that also needs to happen is the particles need to actually hit each other. Okay, particles need to hit each other. So if a particle has enough kinetic energy and it's moving towards another particle, but what needs to happen is they need to hit each other. If they're not going to hit each other, then there's not going to be a successful collision. So they have to have enough kinetic energy, and they also have to hit each other with the correct orientation. They have to hit each other just perfectly. If they hit each other at some kind of angle, then some of the kinetic energy is lost, and therefore they don't have enough kinetic energy. So what needs to happen is they have to have sufficient kinetic energy, and they also have the correct orientation, or sometimes what we can say is the correct geometry. If we have the correct geometry, and enough kinetic energy, then we'll have a successful collision. Okay, so our answer should be D. And remember, B is a very, very wrong answer. Particles convert all their potential energy into kinetic energy. As particles approach each other, kinetic energy is turned into potential energy, not the other way around. Now let's take a look at question number 4. It says, which of the following best describes the EA, or activation energy, of a fast reaction and the stability of its activated complex? EA is activation energy. If the reaction is going to be happening fast, what we can say about it is that it's going to have a very small EA. So if here's a graph of potential energy, okay, and reaction proceeds on here, what we'd see is that our EA would be very, very small. Okay, so what we're looking for is something with a small activation energy. Now, an activated complex, which is at the top right here, is always unstable. It's unstable because it has a high amount of potential energy. Okay, so we're looking for something like this one. So our answer for number 4 is A. It has a small activation energy and an unstable activated complex. Let's look at the next question right here, question number 5. It says, how does the addition of a catalyst increase the reaction rate of an endothermic reaction? Let's start off this question by drawing an endothermic reaction. So what we have here is we have reactants absorbing energy and turning into products. Now, how a catalyst works is a catalyst provides an alternate pathway or reaction mechanism that requires a smaller or less activation energy. So let's draw our catalyzed reaction in here. So what we see is here's our catalyzed reaction. Now, what has happened here is that the products are the same as they were when uncatalyzed. The reactants are the same as they were in the uncatalyzed. But what has changed is the activation energy that is required for the reaction to happen. And that's how it increases the reaction rate. It has a lower activation energy, and therefore the reaction rate can increase. Okay, so this distance right here is the EA of the uncatalyzed. Now, this distance right here is the EA of the catalyzed. Okay, of the reverse reaction. Now, in the forward reaction, this is the EA of the forward reaction. And right here is the EA of the forward reaction. And what we can see is the EA of the forward reaction is much smaller than the EA of the forward reaction of the uncatalyzed. So how it increases the reaction rate is it reduces the required activation energy, 5C. Let's move on to question number 6. It says, consider the following potential energy diagram. And the question says, what is the activation energy for the reverse reaction? So the reverse reaction, again, is moving in this direction right here. If this distance right here is our activation energy of the reverse direction. Okay, so this distance or this height is 20, 40, 60. So 6 should be plus 60. It shouldn't be negative. The only time you should get a negative number is if you're dealing with the change in enthalpy. Okay, but activation energies should always be a positive number. These are all the multiple choice questions for Unit 1. Let's look at some of the written questions for Unit 1. So here is the first written question for Unit 1. It says, using the axis below, sketch a potential energy diagram for the reacting system where delta H is negative 30. So what that means is that it's exothermic, and EA is 50 kilojoules. So it doesn't tell us what potential energy our reactants start at, or where our products finish at. So you can just pick any number right here. So I'm going to pick the number 50 and draw a nice line for my reactants. And it says my EA is 50 kilojoules. So what I need to do is I need to go up to 100 right here. Then it says my delta H is negative 30. So I need to go down. 50 minus 30 is 20. Okay, so again, this distance right here is my EA. This distance right here is my delta H. The next question says, consider the following reaction mechanism. And question A says, determine the overall reaction. So what we're going to do is we're going to look at their three-step reaction and cancel out anything that's not being used. So we see N2O2 can cancel out. They're on both sides here. N2O can also cancel out. And H2 are on the same side, and H2 are on the same side. So determine the overall reaction. So what is left over is 2NO plus 2H2, and this makes N2 plus 2H2O. Now the next question, it says identify a reaction intermediate. Well, what we have here is we have two reaction intermediates. N2O2 is made and then it is used. If it is started with and then it's a product, that's a catalyst. But this is made and then it's used. So identify a reaction intermediate. One of them is N2O2. Also this one too. It's made, N2O is made, and then it is used. N2O is made and then it is used. Okay, so these are our two reaction intermediates.